This is the main Max MSP patch that controls all the MIDI functions and sends the MIDI data into Ableton Live. Inside this patch, there are several sub-patches which operate various user and computer-controlled elements of the music. First, I will give a brief overview of what each section controls and how it functions. Then I will go into some smaller details. The first section of this patch is the transport bar. This section controls the tempo of the song and sends information like bars, beats and tempo to the rest of the patch, making sure all the elements of the music stay in time. The tempo is determined by the mood, making passive moods slower and active moods faster. The transport is activated once the user is hooked into Synapse. Here a -2 object was added to the bars to act as an intro to the song. This will ease the user into the experience by causing a smooth pad sound to play the root chord and a count-in on the hi-hats, so that the user can anticipate the sound, style and tempo of the upcoming song. This section receives all the Kinect data and mood information from the visual interface patch via an Ethernet cable using a UDP receive object. Each section of data, such as a skeletal joint location, is then separated and sent to the appropriate section of the patch. This section is where the key of the song is determined. The root note and whether the song is major or minor is determined by the mood. Once the key is selected, the scale information is sent out into the call object and the modal change object. The call object takes in numbers which represent MIDI notes and outputs only those which fit within the scale, meaning the user will never be out of key. The modal triad object takes the scale information and determines which chords fit within the key. It then outputs this chord once a number or Roman numeral is entered. This information is then sent to the chord subpatch, which collects the notes and outputs them as a list. The next section controls the chord progression based on the user's position in the room and the previous chord. The space is divided into 5 sections, with the tonic section in the middle, the subdominant on the top left, the dominant on the top right, with the bottom left and the bottom right reserved for more obscure chords within the scale. Each section represents one chord at a time, sometimes over multiple sections, changing dynamically depending on the previous chord so that it will always sound good. When the user moves into a new section, the chord will be triggered on the next bar of the song. The ability to allow the user to have full and intuitive control over the chord progression, but also limit them to which chords sound good together, was a significant challenge. Many iterations of the chord progression control were created and scrapped until this chord matrix system was developed. The primary rhythm instrument is based on the idea of a guitar and consists of 2 sections. The first section controls the chord voicing, taking in the basic chord information from the chord patch and expanding it over 6 strings of the guitar neck. The chord is voiced the same as the fretting position that would be used for that particular chord, depending on where the capo is, using the C shape, A shape, G shape, E shape and D shape. The second section controls how the chord is played and works in a similar way to the melody, having 6 vertical thresholds representing the 6 guitar strings. This is controlled by the user's left hand, with the x-axis controlling the strum. The difference between this and the melody is that the x-axis is measured in a body relative way, as opposed to the melody, which is world relative. An interesting part of this section is the speed dial. This takes the information coming from the x-axis and measures the difference every 50 milliseconds, detecting the speed at which the user is moving. This is then translated into the velocity of the guitar string, meaning if the user hits it harder, it is louder. A final addition to this section was the ability for the computer to operate it. This works by counting down from the last time the user has strummed something. After 10 seconds, the computer kicks in and plays a downstroke every bar. The speed at which the computer strums is determined by the tempo of the song so that it fits in time. This is the secondary rhythm instrument. This is based on short piano stabs and can be kept as they are or placed into an arpeggiator in Ableton. This is also controlled by the user's left hand and is activated by placing it underneath a certain threshold on the y-axis, as if they are playing the piano. The inversion of the chord and how high up on the keyboard it is played depends on the position of the user's left hand along the x-axis in the room. The timing is controlled by the piano play subpatch, which turns the note on or off at the nearest 16th note. The lead instrument is controlled by the user's right hand. The X and Y location determine which note is played, and placing the hand forward in the Z location triggers the note so that the user can easily play but not have any unwanted notes sounding when they don't want to play a melody. To allow the user to easily create melodies that sound pleasant, this subpatch takes in the chord information and scale information and arranges an arpeggio of the chord over several octaves in the 9 vertical thresholds across the X-axis. The Y-axis is then divided into 3 sections, with the top section being 1 scale tone above the chord note, and the bottom section being 1 note below, making sure the chord tones in the scale are in the middle section, making it easy for the user to play a strong musical note and easily resolve a phrase. Using the X and Y location to determine the note, and having the Z location play the note, gives the effect of having the user pluck notes out of the air in musical squares. The drums are controlled by this subpatch, which is based on a basic step sequencer. The beat is chosen at random from a selection of beats that fit within the user's chosen mood and the tempo of the song. These beats are stored in the storage device, which has 3 sections to enable the creation of 4-bar loops. One is for the first and third bars, the second is for the second bar, and the third is for the fourth bar, which usually has a fill. The bass uses a similar storage system to the drums and is chosen to fit with the particular drum beat and mood, with an element of randomness. When a stored bass line is chosen, the list is sent into the step sequencer and separated. Each list consists of 0s, 1s, 2s and 3s, with 0 representing no note being played, 1 representing the root note of the current chord, 2 representing the 5th of the current chord, and 3 representing the octave above the root. This was designed so it can fit easily within any chord progression. All of the MIDI information is then routed to the MIDI out section, which sends each other section into the appropriate MIDI instrument track in Ableton Live. The instrument that each section is routed to changes depending on the mood and an element of randomness.
Pick, pose, play. These are the steps needed for the user to interact with the installation. The mood of the piece is selected by picking a color. This determines key and instrumentation. This is done to vary the sound of the installation and to give each user a unique experience. The video below demonstrates how to pose to allow Synapse to skeletally map the user. Color selection changes video color to show the user's choice. Color information is also sent to the second screen using a UDP port. All of this is created using Jitter. Jit.scale bias allows the color of the video to be changed. The edited video is then merged with the original video using the jit.alphablend object to display the user's choice of color. The user's choice of color sends data to the other computer to allow the choice to determine the key and instrumentation. Both computers are linked using an Ethernet cable to facilitate the sending and receiving of data. The R key is set up to change the RGB values back to that of the original image. This allows the R key to act as a color reset button. The user's choice of color sends data to the other computer to allow the choice to determine the key and instrumentation. Both computers are linked using an Ethernet cable to facilitate the sending and receiving of data. The second screen displays visual haptic feedback and instruction. The user controls RGB values of the left and right visual with the X, Y, and Z positions of their hands. This allows colors to be directly related with gestures that control the music, allowing the user to replicate gestures by using the on-screen visual feedback. Synapse def buffer data is taken into the patch using the jit.synapse object. This one-play matrix is then transformed using the jit.luma2ayuv object into a 4-play matrix. The data is then sent from this object to a jit.ayuv2argb object to allow RGB values to be edited. The image is split in two using a jitscissors object, allowing the left-hand axes to control the left-hand image, while the right hand controls the right. This allows the user to control each parameter between the values of 0 and 1, to ensure the image does not receive too much data, which would result in a very unclear image. This patch also contains written instruction on what gestures the user needs to use to interact with the installation. A pick slider object is mapped to the X and Z axis of the head to give users feedback on where they are standing within the interactive area. This is done to encourage the user to move and explore the interactive space. The master reset mentioned earlier also returns the visuals in this patch to their original values. This patch also serves another very important function. It sends the Synapse data to the other computer. This is done to manage the CPU usage and to ensure that no crashes occur while using the installation.